Okay, so one more video here in chapter 18 through 20-ish. This one's going to be about something a little bit different. It's about luminescence spectroscopy. And luminescence spectroscopy is fundamentally different than absorption spectroscopy. We're still going to be doing spectroscopy on molecules here, but what's different about it is the photophysical process involved, okay? Now, I mentioned earlier that in absorbance spectroscopy, there was the ground state, and then the higher lying level in energy is the excited state. That's just what we call these states. And we went from a lower level to a higher level, and that process was called absorption, occurring on a time scale of 10 to the minus 15 seconds, okay? Luminescence spectroscopy is all about what happens after that. And we hadn't talked about that at all. I mean, how do the molecules get back down to the ground state? And there's a number of different ways. Some of them involve luminescence, where light is actually given off by the molecules. They glow, so to speak. And we can actually measure that light, which is given off, and relate it to analyte concentration. It's a very, very valuable method. And it's very, very sensitive, as it turns out. You can even measure single molecules. Now, the three types of luminescence spectroscopies, which are oftentimes used in analytical chemistry, one is called fluorescence, and that's by far the most popular. But there are other methods. One's called phosphorescence and chemiluminescence. Now, we're going to talk after this about fluorescence and phosphorescence. We aren't going to talk about this one all that much, although it's also a very valuable analytical tool. This is not necessarily applied as much as fluorescence is, but what chemiluminescence is the process by which a chemical reaction produces light. And the way it works is, we'll say substance A and B react. Now, obviously, these aren't real substances, but they're just hypothetical, right? A and B react to form what I'll call AB star. AB star is a reaction product which forms, and when it forms, it actually results in an excited state product. So we're up here in the excited state once AB forms. Now, AB wants to seek the lowest energy state, so it drops back down to the ground state, G for ground and E for excited, okay? And when it drops from the higher to lower energy space, it's got to do something with that energy, okay? And it gives off that energy in forms of a photon. So the reaction produces an excited state product. When that excited state product drops back down to the ground state, a photon of energy is given off. This is chemiluminescence. Many of you have seen chemiluminescence before. If you ever have gone to like the camping supercenter and bought some glow sticks for your camping trip or whatever else you do the glow sticks for, what you do to make them work, of course, is you take a glow stick out of the package and then you have to bend it. And that process of bending it actually breaks a small glass vial inside the glow stick, thereby mixing chemicals and starting the chemiluminescent process, the reaction. It's glow sticks or chemiluminescence. Now, these other processes, phosphorescence and fluorescence, are different. The way that both of these work is they're photophysical. You irradiate a sample with a beam of light that sample absorbs. The molecules in the sample will absorb the photons from that light, promoting an electron to a higher energy excited state. That's an absorption event, just like we learned before. Okay, so absorption always precedes phosphorescence and fluorescence, always. Now, what happens after that is that this electron, which was promoted to a higher energy molecular orbital, will relax back down to the ground state. And when it does so, it gives off a photon in the process. Now, the details of exactly how that happens, we're going to cover in a second, okay? And that's actually the difference between fluorescence and phosphorescence, okay? But nonetheless, this molecule will give off a photon, it will glow, and we can collect that light and relate it to analyte concentration. Now, because we're collecting light emitted from the sample, the detector can't be in direct line with the source. And usually, the detector will be placed at 90 degrees to the incident light beam. It turns out fluorescence and phosphorescence also does not occur at the same wavelength. More on that in a few minutes. Now, the working principle behind luminescence spectroscopy is that the intensity of light that's given off can be related to the concentration by a proportionality constant K that can be experimentally determined, okay? So you basically can run standards, if you will, and figure out the concentration dependence of the signal. That will be something that can be typically done in the lab. So this begs the question then, what is the difference between phosphorescence and fluorescence, and what are some characteristics of all these? So we're going to talk about some more transitions in our molecules, okay? More transitions. So the absorption event is from down here in our ground state. Remember, we've got our molecule down the ground state, we've got an electron there, and by shining light on our sample, that molecule will absorb certain frequencies, certain wavelengths, promoting this electron into an excited electronic level. Now notice all these arrows here on the far left represents absorption events. They're pointing from down up, so we're going to higher energy level, and all those arrows are straight, aren't they? You can break out a straight edge or a ruler and draw them in. Any straight arrow on this figure represents a radiative process, one that involves either absorbing or giving off photons. And this is an energy level diagram. I might call it that, but it's also sometimes given a different name. It's also referred to as a Jablonski diagram. But all it really is depicting the cartoon depiction of energy levels in a molecule. And we start with absorption, okay? So we talked about that, lower state to higher state. So again, this is exceedingly fast process, 10 to the minus 15 seconds or less, essentially instantaneous for our point or for our purposes. Now, what happens once we get into a excited state? Once we get up here somewhere, okay? Well, the first thing that happens, let's say we promote up to that level. Now, this is a higher vibrational energy level within the excited electronic state. And it turns out that really, really, really rapidly, after we get up into that higher state, higher vibrational level state, these little squiggly processes right here, I'm trying to circle and highlight them, okay? Those little squigglies are squiggly arrows pointed downwards. That process occurs very, very, very rapidly, okay? Again, on the time scale of 10 to the minus 12 seconds. Now that process is a vibrational relaxation. And what is typically encountered there is that our molecule, if promoted to a higher vibrational energy level, will very quickly seek this lowest vibrational energy level of the excited electronic state within, again, like picoseconds time scale, very, very rapidly, okay? Now, there's a vibrational relaxation, essentially transfers vibrational energy to molecules in the surroundings, things that this molecule under study that's absorbed a photon might collide with, basically, okay? Or something of the sort. This happens very, very, very rapidly. And we end up in this level right here, which is the lowest vibrational level of the excited state. Now, what happens next? Well, one possibility is shown in these arrows right here. And let's take a look at those arrows. First off, they're pointing all down, aren't they? And they're also all straight, which tells me this is a process involving photons. And we're going from a higher level to a lower level. So in this case, the molecule emits light, doesn't it? It emits light, or it's giving off light. The process depicted right there is fluorescence. All these arrows above are fluorescence, all four of them, okay? It's a straight line from a higher excited state down to the lower ground state. The energy gap between the higher and lower state is bridged by a fluorescence photon or emission of a photon from the molecule. The molecule gives off a photon of light energy, it emits it, it's fluorescence. When fluorescence occurs, it occurs in all directions. We say it's isotropic, occurring in all directions. And in addition to that, it's a pretty fast process. Fluorescence lifetimes for molecules are typically measured in nanoseconds. I'll say maybe up to 100 nanoseconds or so. Basically what that means is if you turn off the light bulb that's causing your absorption to occur, within a couple hundred nanoseconds, the fluorescence is over, okay? Still a pretty rapid process. That's fluorescence. Now, what are some other photophysical properties that can take place? Well, there's really a number of others, okay? One, hold on a second. Called internal conversion. And this is basically like this vibrational relaxation that I've already described. It turns out we can go all the way back down to the ground state via a non-radiative process or a squiggly arrow. That's where that energy could be transferred away to surroundings through vibrational energy. This is internal conversion. Once we get up into the excited state, up top, so we go through our absorptive process, we do squigglies down here, right? We can also undergo the process of what's called intersystem crossing. And this one's important to actually understand phosphorescence, okay? Now, intersystem crossing involves moving our molecule from what's called the singlet state to what's called the triplet state. So these are labeled T, these are labeled S. Okay. So what in the world do we mean by singlet versus triplet? Well, it has to do it has to do with what is called the multiplicity of the states. Now, remember back when you were filling in electron diagrams, box diagrams in Gen Chem. Okay, maybe this was like a 1s atomic shell, and you decide that you're going to draw in arrows that look like this. And we said that we had to pair the arrows one up, one down, and that kind of corresponded to the spin the quantum number of plus 1/2 and minus 1/2, right? And maybe an spin quantum number. And that's kind of how we put them into the shells. Okay. Well, it turns out that electrons and molecules are kind of a similar story. You basically put them into molecular orbitals in a similar fashion, just like we did into the atomic orbitals. Okay. So the usual case might be one up and one down, like that. Okay. So it's a plus 1/2 and a minus 1/2 case, just like we had for right, plus 1/2, minus 1/2. So what is the multiplicity? Okay. Well, the multiplicity is found by 2n plus 1, where n is the sum of those magnetic spin quantum numbers. So in this case, the normal case, I would have plus 1/2, and I'm going to add a minus 1/2. Now, of course, if I add those together, I'll just get 0. And 2 times 0 is 0, plus 1 is 1. Hence the term singlet. That's a singlet state, sort of this normal case, right? All right, now what are some other options of things that can happen, right? Well, when we take that electron and we promote it up through an absorption event, if it undergoes this intersystem crossing over here to a triplet state, what basically ends up happening is the magnetic spin quantum numbers for the electron in that outermost level, if you will, end up being paired, having the same spin quantum number, plus 1/2, plus 1/2. So now you add them up, you get 1, 2 times 1 plus 1, oops, so that equals 3. that is a triplet state, okay? So that's what we mean by triplet and singlet. So intersystem crossing is basically this process of going from a singlet to a triplet state. And that's important because these processes, or these arrows right here, all of these from the triplet state, originating from the triplet state, those are phosphorescence properties, okay? So a triplet to singlet transition is known as phosphorescence. It's still giving off light. Notice that these are still straight lines. It's still a luminescent event. It's light given off, but it's phosphorescence because it originates from the triplet state after the intersystem crossing, okay? All right, now what are some differences between fluorescence and phosphorescence? Well, fluorescence is from the singlet to singlet, phosphorescence is triplet to singlet. Phosphorescence is also considerably slower than fluorescence. Fluorescence is fast. Remember I said fluorescence has a lifetime, maybe 100 nanoseconds? Well, phosphorescence generally has lifetimes of microseconds or longer. Now, a microsecond doesn't sound like a lot, right? But that's at least 10 times greater than fluorescence. And oftentimes, phosphorescence lifetimes are much longer. I remember doing an experiment as an undergrad where we actually took some, I think it was like chlorobenzene or something like that. We cooled it down and liquid nitrogen, I believe it was, make it really, really cold. And then we shined some light on it, and gosh, that thing phosphoresced for at least 30 seconds or a minute, as I recall, okay? So phosphorescence is a much slower process in terms of lifetimes of emission of light. But nonetheless, this is the difference between the two. Now, of these techniques, fluorescence is by far the most popular technique analytically, and even single molecules can be detected. It's very, very sensitive. In fact, it's one of the most sensitive methods of detection that man has come up with to make measurements. Now, that sounds like, well, gosh, if that's the case, why don't we use fluorescence for everything, right? Well, it turns out that not all molecules are fluorescent. We'll talk about that here at the end of the slides, and then I'll go back and fill in the blanks. Not all molecules are fluorescent, so there might be we might need to have a good way of keeping track of which molecules are fluorescent and which aren't, and what the relative fluorescence is. And we can do that through something called quantum yield of fluorescence. Quantum yield of fluorescence. The fluorescence quantum yield is really just a measure of how efficiently a substance fluoresces. It ranges from 0 to 1, generally speaking. Okay, now how do we define it? Well, quantum yield is oftentimes given this symbol too. Okay, is the number of molecules which fluoresce divided by the number of molecules which become electronically excited after a photon is absorbed. So it's basically the photons emitted by fluorescence divided by photons absorbed. It's the fraction of molecules after absorption which give off light or re-emit light as fluorescence. Now, if all molecules, 100% of molecules which absorb light emitted a photon, a fluorescence photon, our fluorescence yield would then be equal to 1. Be perfectly fluorescent. And if the molecule just never glowed at all, didn't ever give off any photons, maybe it absorbed, but it didn't give off anything, our quantum yield will be 0. Okay. Now, that makes a lot of sense, kind of as a scorekeeper. So what exactly is a good value for quantum yield? Well, I would say something that has a quantum yield of 0.3 is actually fairly fluorescent. Oftentimes, things that have quantum yield of 0.3, 0.35, you'll actually use those as fluorescent dyes. And what chemists can do with those, have a molecule which is fluorescent, and I'll call that F star, okay, just to show that it's a fluorescent molecule, and A for analyte. Well, what if you have an analyte which is non-fluorescent, but you want to detect it? You want to measure it by fluorescence, but it's not fluorescent. What do? Well, maybe in some cases, you can come up with an organic chemical reaction, usually, chemical reaction of some sort, in which that analyte reacts with the fluorescent substance. And I'll even label that with a fluorescent yellow color, right? It reacts with the fluorescent substance to form a new molecule, which I'm going to call here AF prime. Okay, again, generic molecules, but you get the idea. Now, this product is now fluorescent. It's tagged, isn't it? It's tagged with a molecule F, which was fluorescent. So the product's now fluorescent. So this scheme is called fluorescence tagging or fluorescence derivatization. It's used a lot in modern analytical chemistry, these reactions that people develop for rapid and quantitative tagging of analytes, which are non-fluorescent. And oftentimes that type of scheme is used a lot. So a fluorescence quantity of 0.3, 0.4 is actually not so bad. So what cues might we use to figure out whether a molecule is fluorescent or not? Turns out there are some correlations between fluorescence and molecular structure. Let's talk very briefly about some of these, okay? Molecules which are highly fluorescent generally contain aromatic rings and are structurally rigid. Those are the two key ingredients to being fluorescent in the UV visible region, okay? Molecules that look like this, that have lots of aromatic rings, generally speaking, pretty fluorescent. Now, the structural rigidity is also pretty darn important for fluorescence. The more structurally rigid the molecule is, the better. Okay, there's actually a really cool textbook example. I love to talk about this. It's so much fun. Look at these two molecules. This one's called biphenyl. This one's fluorine. Not the element. It's called fluorine. It's an organic molecule. It's called this because it's very, very fluorescent. Okay. Now, these molecules are very, very, very similar, and I'll basically show you the difference between them. If I have a chance here. Okay, so in biphenyl, we just have one bond connecting the two rings. Now that bond is still there in fluorine, isn't it? But fluorine has a bond here and here to another carbon. In biphenyl, it doesn't have that, does it? It doesn't have that. And that little structural difference makes a huge difference in fluorescence. Now biphenyl is fluorescent. That's a quantum yield of about 0.2. So about 20% of absorbed photons are re-emitted as fluorescence photons. But fluorine has a quantum yield here approaching 1, much more fluorescent. And the reason why is structural rigidity. Think about the consequences of those two extra bonds. Here, we've got a single bond, which is going to be a sigma bond. Around that bond, rotation is allowed. In other words, these two rings on the end, the phenyl groups, they can sort of rotate with respect to one another. There's nothing that stops that. There's a little bit of an energy barrier, but rotation we'd say is allowed, okay? But in fluorine, because of those two extra bonds to that carbon, we lock that entire molecule through covalent bonds, covalent linkages, into essentially planar flat structure, which is very, very, very rigid. There's no chance for rotation. And because of that minor difference, fluorine is much more fluorescent than biphenyl. Now they're both fluorescent, but fluorine's just more fluorescent, it's more rigid, okay? In addition, if you change or you start substituting molecules, that can have a profound effect on fluorescence properties. For instance, let's see, fluorobenzene, bromobenzene, ionobenzene. This grouping right here, we're taking benzene, right, C6H6, and we are substituting one of the hydrogens for a halogen from fluorine, chlorine, bromine, iodine. We're basically substituting a heavier and heavier halogen each time. But notice while the fluorobenzene has a relative fluorescence intensity of 10, okay, this is like a unitless number that just describes the brightness of fluorescence intensity. As we add heavier and heavier atoms, the intensity really drops off. By the time we get to iodobenzene, stuff's not really fluorescent at all. So oftentimes having, so this is known as the internal heavy atom effect. It turns out if you bond a heavy atom in your structure, it tends to decrease fluorescence or have profound effects on fluorescence. But what I'm more or less wanting to communicate here is that if you start substituting these aromatic rings, that can change fluorescence properties as well. All right, so now that we know a little bit more about quantum yield and what types of molecules are fluorescents, let's take a few steps back here and try to understand why, say, structural rigidity is important for fluorescence. So remember I said for fluorescence to occur, we have to go through a cycle. We have to absorb light, get up to an excited state. We squiggly down here pretty quick, and then we emit back down to the ground state, right? That's the cycle. Absorb, squiggly down, emit, right? With vibrational relaxation being the squiggly. That's our cycle for fluorescence. Can occur on nanosecond type timescales, right? So we said that rigidity of our molecule was important. Why is that? Well, what are some other options for deactivation of the energy after absorption? Well, couldn't our molecule, after the squiggly, undergo essentially internal conversion back down to the ground electronic state? Now notice I made that as squiggly, non-radiative, so it's not fluorescent. It's a different process. And if you remember in that discussion earlier, this Jablonski diagram, we said that squiggly back down to the ground state, non-radiative internal conversion, does not give off a photon. And what it involves is transfer of energy that was caused by the absorption, the photon, right? That was absorbed. The transfer of that energy to the surrounding molecules in the matrix through vibrational interactions. Okay, now if that happens, that's an alternate route to deactivate back down to the ground state, isn't it? So couldn't we think of these two routes then as a competition? Fluorescence is one way we can get back down to the ground state. And this vibrational deactivation, internal conversion, is a second way. So which type of molecules do you think might be able to internally convert back down to the ground state? That's the squiggly. Do you think maybe flexibility of the molecule, availability of rotational degrees of freedom, would that be important for non-radiative deactivation? I think it would, right? The more rigid the molecule, it's going to struggle a bit more to vibrationally deactivate it. But if that molecule is free to rotate and bend and twist whichever way it wants, hey, it's got lots of chances to vibrationally deactivate it. So rigidity helps fluorescence because it impedes this other process, which is in direct competition with fluorescence. Okay, so that's a good reason why the rigidity is important. Okay, now let's talk about luminescence spectrometers real fast. Their difference is from those used for absorption. Some similar parts, some different. We're going to take a light source again. Very often, this is a xenon arc lamp because xenon arc lamps provide light in the UV throughout the visible, and they're bright point sources. Those are the ones that were used in the IMAX theaters. It's basically a glass container full of xenon at high pressure. A couple of electrodes, you make an arc, it gives off light. Now, if you ever use a xenon arc lamp, you have to be a little bit careful with them because the xenon arc lamps are filled with high pressure xenon gas. They've been known to kind of like explode, particularly at the end of their lifetime. So you have to be a little careful with them. And if you ever have to like throw one out after replacing it, there's kind of this whole procedure or process that you can go through where you wrap it up in a towel essentially, and then you can like hit it with a hammer and it breaks inside the towel. And there's directions for this procedure. You can look up to do that on your own, okay, if you ever have to do that. But no, they can be a little dangerous. They can explode. But anyway, we direct the light from the light source, usually UV visible broadband radiation, into a wavelength selector. This is a first monochromator. I'm going to call this one the excitation monochromator. It basically is one of those grading instruments, so maybe a prism-based instrument, like we talked about earlier. It selects a very narrow wavelength band. Now we shine the light that makes it through that on our sample. We're still going to place our sample in a cuvette, but fluorescence cuvettes are a little bit different than absorption cuvettes because fluorescent cuvettes need to be optically transparent on all four sides of the cubic cuvette, whereas the ones for absorption only really need to be transparent on two sides, okay, the input and the output window, but the cuvettes for fluorescence are transparent on all four sides. So what we do then is we collect the light at a 90-degree angle, such that the light which is not absorbed just continues through the sample out the other side. We never ever see that light. But the light that is emitted and collected at a 90-degree angle, this is the light that's given off by fluorescence or phosphorescence from the glowing of the sample. We direct that light into a second wavelength selector. I'm going to call this one my emission monochromator. Second wavelength selector to select a narrow wavelength band, then onto our light detector or transducer. That is oftentimes a photomultiplier tube. The output then records our data and gives that data to us so that we can make sense of it basically, okay? So this is the big difference, is the 90-degree angle. And also another big difference is that we have two wavelength selectors, the excitation monochromator and the emission monochromator. Let's see if we can make sense of this, okay? Why do we have two? I mean, the 90-degree angle, that makes a lot of sense, right? Because you don't want to measure absorption here, you want to measure the light given off. So yeah, I don't want to measure that beam, let's let that go over here somewhere where I don't see it. I'm just going to measure the emitted light. It makes sense. But why in the world does this device have two monochromators? Why do I need to have the ability to spectrally select the input wavelength separately and independently from the output wavelength? There's a really, really good reason for this, okay? We haven't talked about it yet, but is there anything that says that fluorescent needs to occur at the same wavelength as absorption? We haven't talked about it yet, but I don't know. I mean, maybe fluorescence occurs at the same wavelength, maybe it doesn't. So let's go back to our Jablonski diagram and see if we can make sense of what's going to happen. We said that the first step in our cycle is always an absorption event, right? So if we follow one of these arrows up, let's see, I lose my arrow, there it is, okay. So we get to that spot. Now that spot here, okay, way back down to the lowest energy as 0, represents a certain gap in energy. There's this delta E energy gap between the ground state and the excited state, specifically the vibrational level of the excited state that I populated here, okay? Now, what did I say happens after that absorption event? Absorption happens very fast, 10 to the minus 15 seconds, and then all of a sudden we're here. These little squigglies happen, don't they? The vibrational relaxation down to the lowest energy level of the first excited, electronically excited state. And then once we get there, if we want to carry out fluorescence, we can. You just drop back down to one of these levels. Maybe also follow this arrow just by random picking, okay? Now, that represents a different energy gap. I'll make this one in blue, just so that we're not saying that they're the same, because they're not. It's a different energy gap, isn't it? Now, which energy gap is bigger? I'll call this delta E gap fluorescence, okay? And I guess I'll call the red one delta E gap absorption, EBS. Which one's bigger? Isn't the red one bigger? It's bigger to me just by looking at it, right? So what does that say about the relative frequency or wavelength of the photons that are involved in this process? Well, if this gap is bigger, it must correspond to a higher energy photon. That must correspond to a higher frequency photon, which corresponds to a lower wavelength photon. Likewise, for the fluorescence case, well, that was a lower energy transition, which means a lower frequency photon, which means a higher or larger wavelength. Because of this, it's starting to look like maybe the fluorescence and absorption do not occur at the same wavelength. And indeed, that is true. Fluorescence generally always occurs at a longer wavelength than absorption. Not the same wavelength, different color, different wavelength, different frequency, longer wavelength. We might say it's red shifted. A common way to describe it. It's red shifted, occurs at a longer wavelength. We shift towards red. That's what we mean by that. You know, why is this happening? Why is it not exactly the same wavelength? Okay. The key are these little squigglies, aren't they? Isn't that the key here? Those little vibrational relaxations back down to the lowest energy vibrational state of the electronically excited state. We kind of like lose some energy there, don't we? And as a consequence of that, almost always we get red shifted fluorescence. Now, on certain cases, you can see fluorescence at exactly the same wavelength. And when you see that, it's called a resonance fluorescence. And it's a good sign that those little squigglies have, those processes have been minimized or else are not available. So say, for instance, you do a reaction in a vacuum or something like that, or you do this experiment in a vacuum. In such a case, you may be able to see fluorescence at a very close wavelength, if not exactly the same as your excitation beam, okay? So we can explain logically from this Jablonski diagram why fluorescence occurs at a redshifted or longer wavelength. And that explains why we use two monochrometers in our spectrometer for fluorescence. And this one is used to select the wavelength that we're going to use for absorption. We shine that light on our sample to get it to absorb it, right? If you don't have absorption, you can't get fluorescence. So we got to shine the right color. This one is used to select the wavelength of emission for the fluorescence. By scanning the output wavelength selector, we can figure out what colors of light or what wavelengths of light are actually emitted by our sample. What wavelengths does the sample emit at? By scanning this second monochrometer, we can figure that out. And just to finish up this video then, show you a result of a typical experiment. And what this is a typical fluorescence excitation and emission spectrum for a dye called fluorescein. And fluorescein, if you ever see it in solution, it's like a bright yellow-green fluorescent marker type color, okay? It's very, very, very fluorescent stuff. And oftentimes chemists love to take the fluorescein molecule, figure out a way to put a particular group on it, a functional group that reacts with analyte molecules so that you can do fluorescence tagging. Very, very popular thing to do. This particular experiment was just dealing with the base fluorescein dye, just the fluorescent part. So what I actually did in this experiment is I went to collect two spectra, an excitation spectrum and a fluorescence spectrum. And what's plotted here is fluorescence intensity versus wavelength. The two different color data series are each of these two spectra. We'll start with the green one, which is our excitation spectrum. So what I did in this experiment is I scanned, let me make it green actually, that might be instructionally useful, okay. So I scanned, for the green spectra, okay, I scanned my excitation monochrometer but I kept my emission monochromator fixed. And specifically, I fixed it at 550 nanometers wavelength because I knew going into this that this dye would emit at that wavelength, or it would fluoresce at that wavelength. So I scanned my excitation monochromator to collect this green data trace. And the green data trace, remember, is an indication of fluorescence intensity. So down near 300 to 400 nanometers, I got some fluorescence, not a whole lot. And then I got in between here 400 and 500 nanometers, and the peak kind of appeared. The intensity of fluorescence took off, and then it dropped back down again once I got out past 500. This peak wavelength, somewhere around 450, I'll say 450, maybe a little over nanometers. Okay. Now, what does that peak correspond to? Well, obviously it's a wavelength, right? That's the first thing we could say. It would be kind of a bluish, almost bluish green color light. But what that really represents is the best wavelength to excite fluorescence. If you want to make this stuff fluoresce, that's the wavelength to use, right? Because you can get the brightest fluorescence if you use that particular wavelength, right about 450. Now, what event had to happen before fluorescence? Absorption, right? So because of this, excitation spectra, which is what we're talking about here in the green, really resemble absorption spectra for the compound of interest. It basically gives you idea of what colors or wavelengths of light this molecule really likes to absorb, because you got to get absorption to get fluorescence. So if you don't shine the correct color light on your molecule, well, maybe you'll impede absorption, and then you're out of luck, no fluorescence then, okay? So you collected an excitation spectrum, which is this green plot, again, excitation spectrum, what it's called, in green. You collect one of these to figure out what colors of light are best to excite fluorescence. That's what it's used for, okay? All right. Now, after I figured out that I should use 450 nanometers to excite, what I'll do is I'll take that excitation monochromator and I'll adjust it to the optimum wavelength at 450, and I'll just park it there. Now, that is again my excitation beam, the first monochromator in my setup, right? And looking back, it's this one right here. So I would set that one up at 450 nanometers for further experimentation and just leave it there, okay? But there's this other monochromator that I could also set. That one measures the emitted light. So let's look at the consequence of doing that, okay? So again, I'm going to park this one at 450, the first monochromator. Now I can scan my emission monochromator. I'm going to use red for this discussion because I don't have orange as a marker option, okay? So I park my excitation at 450, and then I scan my emission monochromator to see what colors or what wavelengths of light are given off. And the resulting data plot is an emission spectrum, shown in orange. Again, this is a measure of fluorescence intensity as a function of wavelength. So what I saw is between 400 and 490, not a whole lot going on. Very, very dim fluorescence. But once I got up to 500 nanometers, boy, the fluorescence really took off. And it went through a peak and then it kind of came back down once I got out in the red, reaching towards 600 nanometers, okay? But it did go through this peak, and it looks like if I try to project what that wavelength might be, somewhere around here, which I don't know, 550, 545 nanometers, something like that, right? Wavelength. I'm just kind of trying to eyeball it, which is not all that scientific, right? But that is my peak emission of fluorescence. So my emission maximum, I might say lambda EM max, occurs right here at 545 nanometers. Now this is the wavelength of optimum emission of light. That's what I'm studying here, right? What light is given off, what light makes it through the emission monochromators detected. This is the light which is fluoresced, or the light which is given off by the molecules when they're glowing or emitting or luminescent, right? And as we, the wavelength of maximum emission and the wavelength of maximum excitation or absorption are not the same. We saw maximum absorption about 450, but maximum emission was 545 or so, right? Not the same wavelength, almost 100 nanometers different. And the difference between these peaks in our spectra is given a special name. It's called the Stokes shift. And sometimes you hear about Stokes shifted fluorescence. Basically, this is what we're talking about, this red shift that occurs from the absorption maximum. And the reason why it all occurs, again, can be found in your Jablonski diagram. These little pesky vibrational relaxation steps cause the red shifted fluorescence. But you know what? This is not such a bad thing, is it? Think about the experiment. Once again, I'm going to shine light on my sample. Now, in that last experiment, I think that was right about 450 nanometers, wasn't it? Kind of like a blue, almost blue-green color. But then my emitted light, was it like 550? That's going to be green, greenish yellow, probably even. Okay. So my excitation beam is blue, bluish. But my emission, I'll call that a green. Different wavelengths, right? That's the point we've been making all along. But this really contributes to making fluorescence a very, very sensitive method. Because think about it, if fluorescence occurred at exactly the same wavelength, might there be some scattering of blue light to our detector that we sense? And our detector would have no way of telling the difference between light that's fluoresced or light which is just scattered by the sample. And if our sample had particles and fibers, that scattering might be enhanced and possibly the scattering could overtake our fluorescence signal. And we can't tell the difference, it'd be very noisy, right? But because the fluorescence occurs at a different wavelength, far away even, right? Almost 100 nanometers in our case here. Because that's the case, because fluorescence occurs at a different wavelength, this is like awesome because I can use this output wavelength selector to remove the excitation light or beam completely, more or less, and only collect the color which is fluoresced, the green light. And this is wonderful because I get rid of the light from my light source that has nothing to do with my analyte concentration. And I only measure the emitted light, which has everything to do with my analyte concentration. And I measure that emitted light against a very, very dark background, zero background, because no analyte, no green light. It's that simple, right? So luminescence spectroscopy, particularly fluorescence, is extremely, extremely, extremely sensitive. Again, single molecules can relatively easily be detected by this method, provided those molecules are fluorescent, okay? So this is an overview of luminescence spectroscopy. Next video, we're going to talk about atomic spectroscopy, give you a little bit of an overview of that technique.